Hello everyone, welcome back to this online class. Today we are going to look at ODEs of the first order and first degree. In particular, we are going to look at how to solve Bernoulli's equation. Now we are given this example. We are asked to solve the following differential equations. In part A, we have dy over dx plus y is equals to x times y raised to 4. In part B, we have dy over dx plus x times y is equals to x over y cubed. And this is subject to the condition that when x is equals to 0, y is equals to 2. And finally, in part C, we have x times 6x squared minus y minus 1 dy plus 2y times dx is equals to 0. So all those equations are Bernoulli's ODEs. Now, before we look at how to solve each of the equations, let me give you the general form of a Bernoulli's equation of the first order and first degree. So you can write a note that in general, a Bernoulli's ODE of the first order and the first degree takes the form dy over dx plus p of x times y is equals to q of x times y raised to n, where n is not equal to 0 and also n is not equal to 1. Because when n is equals to 0, it means the equation is linear. And when n is equals to 1, the equation is separable. So we require that n is not equal to 0 and also n not equal to 1. I've explained that the case where n is 0, we talk of a linear ODE. The case where n is 1, we talk of a separable ODE. So this is a general form of a Bernoulli equation. It is nonlinear. That equation is nonlinear, and so you must be able to convert it to a linear ODE even before you solve it. I'll tell you how to do that. It is nonlinear. Another for this, the first form. What if we change the roles of x and y? You could have dx over dy plus p of y times x is equals to q of y times x raised to n. N not equal to 0, n not equal to 1. So these equations are non-linear. They are non-linear. These are non-linear. And so you have to convert them to linear ODE. For you to convert this equation to linear ODE, you will use the substitution that z is equals to y raised to 1 minus n. If you want to convert it to a linear ODE, you start by saying let z be equal to y raised to 1 minus n. So that proof again of how to convert a Bernoulli's equation to a linear ODE is available in my PDF notes. You can go through at your own time. Now let's go to the solution. Let's see how to solve part A. So I'll write here, I'll write the same equation. We have dy over dx plus y is equals to x times y raised to 4. So what you do, you must get rid of the function of y from the right-hand side. I want to convert it to a linear ODE. So what will I do? Divide through by y raised to 4. Because I want to get rid of the y's from the right-hand side. So this means my equation will now be written as, remember it is, take note so that we don't write so many things, that 1 over y raised to 4 is the same as y raised to negative 4. So it's like we are multiplying the equation by y raised to negative 4, so that we get, you can write this implies that y raised to negative 4 plus, not plus, this dy dx plus, what is y times y raised to negative 4? That will give us y raised to negative 3 is equals to x. Y raised to negative 4 times y raised to 4, that is 1. So x times 1 is just x. So I've divided by y raised to 4, or you can also say that we have multiplied by y raised to negative 4. So now, once you are here, we are going to replace this one by z. If you let z to be equal to, let this be equal to z, what should this term look like in terms of z? We need to replace those two terms. So we start by saying let z be equal to y raised to negative 3. So from here, it means that dz dy is equals to negative 3 times y raised to negative 4, power rule of differentiation. So you can say that therefore, if I want dz dx, chain rule will give us dz dy times dy dx. And so this is the same as dz dy is negative 3 times y raised to negative 4 times dy dx, which I don't know. And you see, y raised to negative 4 times dy dx is the first term in our ODE, so I need to make this the subject. Look at this. Y raised to negative 4 times dy dx. So from here, it simply means that y raised to negative 4 times dy dx is the same as negative 1 over 3 times dz dx. Somebody might be wondering, where am I getting negative 1 over 3? Remember, here we had dz dx. So when you divide by negative 3, you get what we have here, negative 1 over 3 times dz dx. So we are going to make this substitution here, this one, and also this. Those are the substitutions we make, this and this. So therefore, this equation can now be written as, here we have negative 1 over 3 dz dx. The other one is z is equals to x. But you must ensure that the coefficient of the highest derivative is 1. Instead of negative 1 over 3, let's make it 1. So I'm going to multiply this equation by negative 3 on both sides, so that we are going to get, when you multiply by negative 3, you're going to get dz dx minus 3z is equals to negative 3x. So this is now linear in the dependent variable z. Remember, initially it was non-linear, but now once we have made that substitution, we now get a linear ODE in the new dependent variable z. So I'll comment on this one and call it, you say linear ODE in the new dependent variable z. Let's call it equation star. This one, let's call it equation star. So look at the coefficient of z. This is what we are calling p of x. I need to integrate it. So you write the integral of p of x dx, that is equals to the integral of negative 3 dx, which is simply equal to negative 3x. So now the integrating factor is exponential integral of p of x dx. That will be exponential negative 3x. That's what we have found as the integrating factor. Now, multiply the ODE, multiply equation star by the integrating factor. Multiply equation star by the integrating factor. So what do we get? We'll write here exponential negative 3x times dz dx, then minus 3 exponential negative 3x times z is equals to negative 3x exponential negative 3x. So that's when you multiply by the integrating factor. Now remember, equation star is linear. So the left-hand side can be rewritten as the derivative with respect to the independent variable of the product of the dependent variable and the integrating factor. So it can be written as this one. Derivative with respect to x, that's our independent variable, of the product of z and exponential negative 3x. Dependent and integrating factor. So that on the right hand side we need x, we should get 3x exponential negative 3x. Or if I multiply through by dx, I'm going to get dz times exponential negative 3x is equals to negative 3x exponential negative 3x dx. So now you can integrate both sides. And on the left-hand side, we have integral and derivative. Remember, they're inverses of each other. So here we expect to have z, let's use another color. We expect to have z times exponential negative 3x is equals to, on the right-hand side, how do we integrate? Look at here, we have a product of two functions. This is negative 3x is algebraic. The other one is exponential. So we are going to use integration by parts. Let me divide this. So that integration by parts, u will be negative 3x. The rest will form dv. So that is exponential negative 3x dx. But again, you realize that this u here is a polynomial. When u is a polynomial, then it is better to use tabular integration. Tabular integration is faster than the integration by parts. So all we need is u in the first column and dv over dx in the second column. So our u is negative 3x. dv dx is exponential and negative 3x. So the first column we are going to differentiate until we get to 0. The second column you integrate. So now the derivative of negative 3x is negative 3. The integral of exponential negative 3x is negative 1 over 3 exponential negative 3x. Derivative of negative 3 is 0. The integral of negative 1 over 3 times exponential negative 3x is the same as 1 over 9 exponential negative 3x. So once you're there, we stop, and then we link these terms, only two arrows, so that the sign here is a positive, here we have negative. So that means on the right hand side of this integral, or a solution here, let me explain those arrows here. So the first arrow here means you take negative 3x, positive times negative 3x times negative 1 over 3 exponential negative 3x. So that arrow means you multiply everything that you have there, and the sign is positive. Positive, this negative here times another negative here, that's another positive. So positive times negative will give you a positive. So that is positive 3x times 1 over 3 exponential negative 3x. Then here, this negative, this times negative 3, that's positive 3 times 1 over 9. So we have another one, positive 3 times 1 over 9 exponential negative 3x plus a constant c of integration. And you see this can be simplified so that we have x exponential negative 3x plus 1 over 3 exponential negative 3x plus c. I can see exponential negative 3x is common, so it is x plus 1 over 3 times exponential negative 3x plus c. C is a constant of integration. Make z the subject. So you can say, or z is equals to x plus 1 over 3 plus c over exponential negative 3x, which if you take it up, you get c times exponential 3x. The negative now becomes positive. Laws of indices, that's what I've used there. And now that's our solution, but you have to replace z because you have to go back to x and y. So where did we define z? We go back, check where we defined z, and we said z is equals to y raised to negative 3. So replace z by y raised to negative 3 to get the final solution, the general solution. So we write put z is equals to y raised to negative 3. So that we are going to get this. Therefore, y raised to negative 3 is equals to x plus 1 over 3 plus c exponential 3x. So this one here is our general solution. Remember, we don't have conditions to apply here. And so this is the general solution. Let's solve part B. In part B, what was the question? You can go back and check. Our question in part B is dy over dx plus xy is equals to x over y cubed. And the condition is that y0 is equals to 2. That the value of y is 2 when x is equals to 0. Again, this is Bernoulli's ODE. We have to get rid of the y cubed. Remember, take note that 1 over y cubed is the same as y raised to negative 3. So for me to get rid of that y cubed, I have to multiply the whole of this equation by y cubed so that I get rid of the y from the right hand side. I expect that the right hand side should be purely functions of x only. There should be no y on the right hand side. So how do we get rid of the y cubed from the right hand side? Is that this equation I'm going to multiply by y cubed on both sides so that we have y raised to 3 dy dx plus x times y raised to 4 is equals to x. That's what we get if you multiply by y cubed. Now, we need to transform this equation to a linear ODE in the new dependent variable z. So this one is z. Now, if that is z, then what will this be in terms of z? So we say let z be equal to y raised to 4. So from here, it means derivative of z with respect to y is equals to 4 times y cubed. That's what we have. Now, I want to use chain rule. So you can say, therefore, if you now want dz dx, using chain rule, that's the same as dz dy times dy dx. That's chain rule. I know dz dy to be 4y cubed. Then here we have times dy dx, which I don't know. Just write the way it is. Now look at our equation, this one. The first term is y cubed times dy dx. We can get it from here now. Make this the subject. Remember here we have dz dx. So I have to divide by 4. So this means that where we have y cubed dy dx, that's the same as 1 over 4 dz dx. So that's a substitution that we need to make. This one. Another substitution is this. Those two that are bracketed, those are the substitutions that we need to make to transform our equation to a linear ODE in the dependent variable z. So this one will now be 1 over 4 dz dx, then plus x times z is equals to x. But you must ensure that the coefficient of the first derivative is 1. So we have to multiply this equation by 4. Multiply by 4 on both sides to get dz dx plus 4xz is equals to 4x. Now, this equation, let's comment on this. This equation is linear ODE in the new dependent variable z. Of course, our independent variable is x. So you solve it using the integrating factor method. Look at the coefficient of z. It is positive 4x. So this one here is our p of x. That's positive 4x. So we need to integrate it. So the integral of p of x dx. That's the integral of 4x dx, which is simply 4x squared over 2. That is simply 2x squared. 2x squared. Don't write the constants of integration. The next thing, you get the integrating factor. Integrating factor, that should be equal to exponential the integral of p of x dx. And so that is exponential. That integral was 2x squared. So this is our integrating factor. Now, the next step is you need to multiply the ODE. Let's call it equation star. Let's call this is equation star. So multiply equation star by the integrating factor. So what do we get when we multiply with the integrating factor? We are going to get this exponential 2x squared dz dx plus 4x times exponential 2x squared z is equals to 4x exponential 2x squared. That's what we have. Now take note how the left-hand side can be rewritten. Remember, we have explained this, that once you have multiplied a linear ODE by the integrating factor, then the left-hand side can be rewritten as the derivative with respect to the independent variable, in this case it is x, of the product of the dependent variable, which is z, and the integrating factor, which is exponential 2x squared. So that's what we get on the left-hand side. The right-hand side is 4x exponential 2x squared. Now, if I multiply both sides by dx, we are going to get d of z times exponential 2x squared, that should be 2x squared, is equals to 4x times exponential 2x squared. Now you can integrate both sides. If you look at the left-hand side, you realize that we have this integral and derivative, which are inverses of each other. So those two will cancel out, so that what you remain with on the left-hand side is z times exponential 2x squared is equals to. Now on the right-hand side, you're going to use u substitution. Let u be equal to 2x squared. Let u be equal to 2x squared. This means du dx is equals to 4x. Or you can make du the subject, or du is equals to 4x dx. Remember, when you are dealing with ODEs, you must be conversant with all those techniques of integration that you learned in calculus, that is integral calculus or calculus 2. Because we are applying those concepts, those techniques of integration, to be able to evaluate ordinary differential equations. So now, this can now be written as the integral of exponential u du. You're saying where we have 4x dx, that is du. Look at this, 4x, and there was dx here, which I didn't write. So 4x times dx, that form du. So when you integrate this, what do we get? Exponential u plus a constant c. But you have to replace u. So when you replace u, that is exponential 2x squared plus a constant c. Remember, the constant must be added at the final solution. So when you make z the subject, what do you get? You get z is equals to 1. We are dividing by that exponential function, then plus c times exponential negative 2x squared. So this is our general solution, but we have to replace z. So check where we defined our z and you substitute it. So you write put z is equals to, what was it? We said z is equals to y raised to 4. Let's just confirm. So we are going to substitute where there is z, we put, it was this one, y raised to 4. So that is the substitution that we need to make here. Put z is y raised to 4. So that therefore, we now talk of y raised to 4 is equals to 1 plus c times exponential and negative 2x squared. So this one is our general solution. This is our general solution. We now need to find the particular solution. So let me comment general solution. The c that we have there is an arbitrary constant, which we need to determine its value when we apply the given initial conditions. So let's see, what was the initial condition? It was that the value of y when x is 0 should be equal to 2. So you write apply the initial condition, apply the condition that y0, y of 0 is equals to 2. So what does it mean here? That when x is equals to 0, y should be equal to 2. That's what it means. So let's substitute. Where there is y, you put 2. Where there is x, you put 0. In our general solution, so we are saying 2 raised to 4 should be equal to 1 plus c times exponential 0. Anything raised to 0 is 1, so this simply means that 16, that is 2 raised to 4, is equals to 1 plus c. So when you make c the subject, you get c is equals to 16 minus 1, that will give us 15. So now go back and replace it in our general solution. So you can just say that therefore, y raised to 4 is equals to 1 plus 15 times exponential negative 2x squared. So this that we have found here finally is our particular solution. So let's comment on this again. You talk of particular solution. So that is part B. We still have one section remaining, part C. So in part C, again, we are going to write the equation that we have been given. So the equation in part C is, let me write it down here. That was x times 6x squared minus y minus 1 times dy plus 2y dx is equals to 0. So we can write x times 6x squared minus y minus 1 dy plus 2y dx is equals to 0. So that's what we have. Now, this equation, it can be rewritten in the form of dx over dy. Let's see what you're going to get. If I divide both sides by dy, also here by dy, even this, so that this dy will cancel. So you can say that this implies that x, of course, this is now 6x cubed minus x into y plus 1, then plus 2y dx over dy is equals to 0. I also need to make the coefficient of the derivative to be 1, so divide by 2y on both sides, 2y over 2y. Again, this one is over 2y. So that we can write this as 3x cubed over y minus x over 2y times y plus 1 plus dx over dy is equals to 0. Let me rearrange this equation. We can say or dx over dy minus, this is now y plus 1 over 2y times x. Then now we'll have is equals to negative 3 over y times x cubed. So when we rearrange, we are going to get that one. Now, this equation is a Bernoulli's equation. Look at the dependent variable is x, and we still have x on the right hand side. So this is Bernoulli's equation. And in this case, our dependent variable is x, not y. So we look at the second form of the Bernoulli's equation, how to solve it. So this equation can also be written as, if I simplify this one, I want to divide by y, so that that equation can as well be written as dx over dy minus 1 over 2 into 1 plus 1 over y times x is equals to negative 3 over y times x cubed. So that's what we have. Now, let's transform this equation to a linear ODE. Linear ODE in the new dependent variable z. So we are going to make the substitution, or before we make the substitution, I need to get rid of the x cubed from the right hand side. So what we do, we divide the entire equation by x cubed. Or dividing by x cubed means that multiplying this equation by x raised to negative 3. Because we said 1 over x cubed is the same as x raised to negative 3. So dividing by x cubed is the same as multiplying by x raised to negative 3. So when you multiply through by x raised to negative 3, we are going to get, let me write, this implies that if I multiply by x raised to negative 3, I'm going to get x raised to negative 3 times dx over dy, then minus 1 over 2 into 1 plus 1 over y times x raised to negative 2. Of course, there's another x here raised to 1. So loss of indices, that will be negative 2, is equals to negative 3 over y. Now, we now let this be equal to z. We need to know what will be this first term in terms of z. So you say let z be equal to x raised to negative 2. So when you differentiate, you get dz dx is equals to negative 2 x cubed, x raised to negative 3, I mean, sorry. Now, I need dz dy, so you can say therefore Using chain rule, the z dy is the same as dz dx times dx dy. I know dz dx to be -2 times x raised to -3. Then there's times dx dy, which I don't know. Now look at this term, x raised to -3 dx dy. We can get it from here. Make this the subject. Remember here we have dz dy. So I love to divide by -2. So you write or x raised to -3 dx dy is the same as -1/2 dz dy. So that is the substitution that you need to make where we have the derivative for this. And also another substitution is z is equals to x raised to -2. Now, let's come back to this equation. Here we have found -1/2 dz dy, then minus 1/2 1 plus 1/y z is equals to -3/y. That's what we have. And so you need to make the coefficient of the derivative to be 1. So what do? Instead of -1/2, make it 1. So this we are going to multiply by -2. So therefore, dz dy plus 1 plus 1/y times z is equals to 6/y. Now this equation is linear in the new dependent variable z. So let me comment on this. And you write this is linear ODE in the new dependent variable z. And our independent variable is y. So the coefficient of z is our p of y. So this one is our p of y. So I need to integrate it. We need now the integral of p of y dy. That is the integral of 1 plus 1/y dy, which is the same as y plus natural log of y. So that's our integrating, not integrating factor, but the integral of the coefficient of z. So we can now find the integrating factor. Integrating factor is equals to exponential of the integral of p of y dy. That's the same as exponential y plus ln y. And this is the same as writing exponential y times exponential ln y. This can be written as y times exponential y. So that's the integrating factor. Now, let's multiply the whole of this equation by the integrating factor. So let's call it equation star. This one, call it star. Then you write multiply multiply star by the integrating factor. So what do we get? On the left, we'll have, let me use another color, y exponential y times dz dy, then plus 1 plus 1 over y times y exponential y z is equals to 6 over y times y exponential y. And so we can simplify. Look at the left-hand side. How will it, or how can it be rewritten? So this can be rewritten as the derivative with respect to the independent variable. In this case, our independent variable is y, of the product of dependent variable, which is z, and the integrating factor, which is y times exponential y. On the right-hand side, you see this and this will cancel. So we only have 6 times exponential y on the right-hand side. So if I multiply, right, this implies that if I multiply both sides by dy, we are going to get derivative of z times y exponential y is equals to 6 exponential y dy. So I need to integrate both sides. On the left-hand side, this is integral, this is derivative. Those are inverses of each other, so they'll cancel out. So that what we have here is z times y times exponential y is equals to 6 exponential y plus a constant c of integration. So, or, you see this, you could also write as z times y is equals to 6 plus c times exponential negative. What have I done? I have divided this by exponential y. Everywhere, this by exponential y, even this by exponential y. So that I get what I have there. That is our general solution, but you have to replace z. So where did we define our z? Go back and check. In the substitutions, we said let z be equal to x raised to negative 2. This one. So we replace z by x raised to negative 2. Let's see what we are going to get. So you can write here that put z is equals to x raised to negative 2. So when you make that substitution, what do we get finally as our general solution? So this is what you're going to get. You say you can write therefore, instead of z, we are going to write x raised to negative 2. So we'll have x raised to negative 2 times y is equals to 6 plus c times exponential negative y. So the c that you see there is an arbitrary constant. It is the constant of integration. So what you have found here is the general solution. So you can comment on this one and say this is the general solution. So that's how to solve Bernoulli's equations of the first order and the first degree. Thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in ODEs of the first order and first degree. Bye-bye.